Yeah, it's about side channel attack. So what's a side channel attack? You get some encrypted data. There's a decryption process inside your computer, right? That plain text you may keep in memory. You may write that to text file, database, or whatever. You can do whatever work. So in that case, that file, memory, or if you are transferring that data to network or writing it to disk or something, that is called main channel, right? That channel is specifically implemented for you to work, right? That's the main channel. However, when this process runs inside the computer, data leaks out from some unintended channel. For example, timing information, power dissipation of your device, electromagnetic radiation created by the electronics being operated inside the machine, and light generated by your monitor. Right? Those channels, you don't really consider them as communication medium. You don't pay attention. You don't even think those channels can transmit any useful information. Right? So when any electronic device operates, it creates some kind of electromagnetic energy. So our computers also generate that kind of electromagnetic energy, but we don't think that kind of energy can transmit any useful information. We don't expect it. But that's not the case. If attacker has access to your ciphertext and he has sufficient facilities to extract data from these unintended channels, he can actually attack the computer and even find your secret keys. So this is some kind of area that people have started research very recently. So what are these other channels that you can steal information from, that some attacker can steal information from? Right? You have your process, input and output. So your output is your main channel. Input and output goes to your main channels. Your network, Bluetooth, Wi-Fi, or whatever the facilities provided to your device. Right? And there are some unintended channels as well. Power consumption, electromagnetic emission, timing information inside your cryptographic algorithm. Right? If there is a branch taken, if you are programming if is taken, if the condition is true, program goes to one branch of code. If it is false, it goes to another branch of code. So amount of time that these two branches need can be different. Even that information can be used to extract cryptographic keys from your device. Also sound, heat, and inherent design faults in processor electronics. So let's go through a few of these. I'm not going to cover every single thing, but let's go through a few of these. First is electromagnetic radiation. So I'm going to do a little demonstration. So I wanted to actually do few demonstrations in this presentation, but unfortunately I didn't have enough equipment to do that. So this is the only one demonstration I can do. So there's a software created specifically to demonstrate that electromagnetic radiation emitted from your monitor can carry useful information. when a monitor operates, it emits some kind of electromagnetic radiation. Can we use that radiation to transmit any useful data? Right? Any kind of useful information. So this program was created in order to demonstrate that. It's called Tempest for Eliza. Tempest is actually a security standard, right? Telecommunication, electronics material protected from emanating spurious transmission. That's a security standard that regulates electromagnetic emissions from the device. So the person who created this program named it after this security standard. It's basically you are giving a few parameters, right? If you consider your monitor, there's a particular way that it works. You send video signals to your monitor. It doesn't actually show you a picture. It doesn't show the entire picture at once, right? It basically scans. It starts from here, scans from there, scans to that corner, then move to second line, scan that to other corner, likewise scans down. At any given time, it only shows one pixel, right? So there's a continuous data stream going to your monitor, and it has built-in electronics to this scanning process. This first parameter is the clock frequency that operates in the monitor in order to do the scanning process. Next one is horizontal resolution, then vertical resolution. There is another parameter called H, total size. That also you can calculate. If you know horizontal and vertical resolution of the display, you can calculate pixel frequency and the total size. So here is a basic chart. For example, for this monitor, its resolution is 1920 by 1080. Right? For that monitor, pixel clock is 148.5 megahertz. Then you have to do a radio frequency and an MP3 file. Right? What it does is it creates specific pattern on this monitor so that it transmits this MP3 file through the electromagnetic radiation. Right? That signal you can pick up using this kind of radio. This is my mom's radio. I got to for your demonstration. Let's try it. It only operates on the primary monitor, so I'm going to disconnect the projector and connect this to the monitor. So I wanted to do this demonstration physically here, but I wasn't able to find equipment for that, so I will show you a video.
Hi, my name is Gary Kenworthy, and I work at Cryptography Research. We use encryption every day: electronic payments and banking transactions, encrypted storage, premium content protection. These are just a few of the applications in which our mobile phones, PDAs, and tablets use secret cryptographic keys to protect sensitive or secret information. At CRI, we set out to test mobile devices to see how secure these operations might be. We expected to find some leakage, but what surprised us was the extent to which these devices leak. These mobile devices all have radios for wireless communications, cellular, Wi-Fi, Bluetooth, and the like. But these radios are not the sources of the leaks that we're finding. In fact, we put the devices in airplane mode to turn all of the radios off. This unintentional electromagnetic radiation can be picked up using a common radio receiver. By digitizing and analyzing these signals, we can extract and decode the secret keys used in the cryptographic algorithms. Leakage signals can be picked up by a probe that's as simple as a loop of wire that responds to the magnetic field coming from the device. This wire loop is connected to the radio's antenna input. The radio intermediate frequency output is connected through a home-built amplifier to an inexpensive digitizer. We've written our own application that calls standard crypto libraries, and we've installed it on this phone. I'm now going to make it run RSA operations in a loop. On the computer screen, we have several displays. This one shows the radio spectrum centered around the frequency that the radio is tuned to. As I move the probe around the phone, we see energy fluctuations of the magnetic field coming from the phone. When we see an interesting signal, we can tune the frequency and the position of the pickup loop to maximize the signal. We also adjust our bandwidth to give us a better display. Now we look at the signal in the time domain. This is like an oscilloscope. We can begin to see patterns in the signal. Notice the sharp vertical transitions representing sudden increases and decreases in radiated power. The two large power blocks with a short drop in the middle is a characteristic of the Chinese remainder theorem implementation of RSA. Zooming in on the individual operations, we discover even more. In this magnified time view, we again see sharp vertical transitions and varying durations of increased power radiation. We also notice that the duration of each pulse varies. This is the way that the signal that we are seeing reveals the secret bits of the key. The pattern reveals that each 1 in the secret exponent consists of a squaring step followed by a multiplication step, while a 0 in the exponent involves only a squaring step. So, with a single trace, we can directly read each of the secret bits and completely recover the secret key. Secret cryptographic keys can also be recovered from a distance. We will use this antenna connected to the input of our radio receiver. We've written our own application which performs elliptic curve point multiplications, which are part of ECC cryptography. I'm now going to begin those operations in a loop. As the crypto is started, we can actually hear the operations. But it's also interesting that we can hear it and recover the secret key from a distance. The transitions we see here represent the double and add components of the elliptic curve operations. Looking at the plot, we can see that the double takes less time than the add. A double operation by itself represents a 0 bit, and the double operation followed by an add represents a 1. In being able to read this sequence, we can recover the entire secret key. We believe that it's important for mobile phone hardware, software, and operating system developers to be aware of these vulnerabilities. We at Cryptography Research have developed hardware and software countermeasures to protect against this kind of leakage. We hope that this demonstration has informed and educated you on the exposed nature of mobile devices. Thank you.
Basically, these side channel attacks are going to be a real threat now and in the future. Right? People are now discovering details about this side channel analysis, and each day they come up with various sophisticated mathematical algorithms that they can use to extract and analyze this data and get some useful information out of it. So this is another experiment, right? You are familiar with PS2 keyboards, right? You might have used those PS2 keyboards before USB ones. Now, with this experiment, they are trying to steal information from the keyboard itself. So, typing in the keyboard, that information is transmitted to the computer through the PS2 adapter, through a wire, right? That wire has actually 4 different cables inside, 5 with the shield, right? Data cable, clock cable, voltage for the keyboard to run, and the ground, right? Around those 4 wires is a shield. That shield is connected to your earth wire. I think you have done some physics at school, so if you don't understand any of this, now there's an earth wire, right? If you look at any power socket, there are 3 wires that you can connect it to. One of them is earth wire that is connected to ground. It doesn't carry any electricity. Compared to neutral one, it is connected to ground. If there is any leakage, earth wire conduct that electricity to ground. That's the idea. Right? It's neutral one. However, with any electronic equipment, chassis and these shields are connected, ultimately one connected to the earth wire. Then what happens is, if you type something into your keyboard, electrical signal is generated and transmitted through this wire. When electrical normally these signals are in radio frequency range, right? When electrical signal transmits inside these wires, it induces electromagnetic energy in the shield, right? This electromagnetic energy is actually leaked into the shield. Through the shield, it can go anywhere inside the building through the earth wire. In that case, it's earth wire acts as an antenna. If you have set up a computer with PS2 keyboard here, you might be able to pick up this signal from another room or another floor, because earth wire is connected to the same electrical circuit in the building. So they have developed this experiment. You have your PC, PS2 keyboard connected, and you have your earth wire, right? So earth wire is connected to ground. If you know something about electricity, this earth wire is at volt 0. What they do is, they create another reference ground and connect a resistor to this earth wire. So this reference ground is also at voltage 0. Earth wire is also at voltage 0. Then through this resistor there can't be any voltage, right? According to theory. But that's not the case. Right? There are other theories that we have forgotten. So this basically electromagnetic radiation is leaked into the earth system. It actually generates small voltage across this resistor. That voltage can be measured by analog to digital converter. So this is the reference ground. So other end of the resistor, Vref, they connect it to a pipe. Basically in the US, these metal pipes are separately grounded. So it's very good. Pipe system acts as very good earth, so they can use it as a reference ground. So this is the signal they recorded using analog to digital converter. We can't see anything here. It's just noise, right? It's white noise. After that, that's the signal they recorded at the top. Then they digitally filter out that signal. Normally, signals that goes inside the PS2 cable are in the range of 10 to 16.7 kilohertz. So they filter out all the high frequency signals and let the low frequency signals only in this range pass through the filter. There are software filters that you can apply if you have done digital signal processing. There are software filters that you can apply. For this purpose, they have applied band pass filter. Band pass filter only let this specific band passes through it and cut all other frequencies. So then they extract this low frequency in 10 to 16.7 kilohertz. right? From that noise, let's see this magnified view of that signal. Let's see what the signal is. So, the top you can see the data how the PS2 keyboard transmits data. There is a clock. Clock signals the system to transmit bits one by one. Right? There's a start bit, and a data bit, parity bit, and stop bit. If you know anything about electronics, you can understand this. Basically, each bit has a dedicated time slot. Right? In that time slot, if the voltage is 1, or if the voltage is 5, we take that as bit logic 1. If the voltage is 0, we take that as logic 0. Right? So, if you press the key on the PS2 keyboard, it transmits this signal. Basically, 8, 9, 10, 11 bits. So this is the basic signal transmitted to PS2 cable. This is what we have recorded and filtered out. So if you separate this to individual bit windows, this is what we get. Right? 3 zeros, 3 ones, 4 zeros and 1. If you interpret this data, it's like this. Right? This is 28. Normally, so for these letters, we use ASCII code, right? But inside the keyboard, there's another standard called scan code. So letter A, what is the ASCII code for capital letter A? 65. But the scan code is 28, this different scan. So now they can extract letter A being transmitted by monitoring the earth wire somewhere else. This is another form of side channel attack. You have your computer here. From that room, someone can monitor your keyboard without installing anything in your computer. Someone can take this further, right? That was a lab setup, but there are cheap microcontroller boards available now with analog to digital conversion built in. Someone can actually develop a device that they can plug into any wall socket and do this process continuously. Right? There's an analog to digital converter. It converts it acquires the signal from the earth wire and filter, process it, and extract to individual keys and write it to a SD card or something. If you can spend about $150, you can develop a device like this. It's only a matter of software. It's very simple hardware, right? There's no sophisticated hardware. Everything is software. After you have, you can actually buy a simple microcontroller board for this. That is electromagnetic radiation. So another form of side channel is power analysis. You have seen smart cards, right? Normally smart cards, there are cryptographic keys are programmed inside the smart card. You can't take that keys out. Right? Anywhere, they are safe. Cryptographic key is inside the smart card. If you want to encrypt or decrypt anything, you send that data into the smart card. Electronics in the smart card decrypt the data and gives you plain text. Key is never transmitted anywhere. It's inside the card. So how can I retrieve a key from that kind of smart card? People can do that using a power analysis. Right? What they do is they send different ciphers, different data to smart card and let it do the encryption process. So oscilloscope or some electronic equipment and monitor the power usage of that device. When the electronic device operates, it draws current. It uses some power. We can continuously monitor the power usage. Right? What we can do is we add a resistor in series with the power supply and monitor the voltage across the resistor. Right? If you know the voltage, P equals VI, you all know that equation, then you can actually calculate the power. Right? If you know the voltage, power is V squared by R. R is the value of this resistor. Now, I'll do another demonstration video. Before that, I'll give some background information about AES, because you need this information to properly understand you. So, very simply, AES process is like this. There are several steps, right? State is your plain text input data, and you have your cipher.
Hi, my name is Elke de Mulder, and I'm an engineer working at Cryptography Research. We are a security research and development company focused on solving some of the most complex data security problems for eliminating fraud, piracy, and counterfeiting. Whenever a security device uses secret cryptographic keys to protect sensitive data or transactions, information about the secret keys can leak out from the device's power consumption or electromagnetic emission. Unfortunately, attackers can examine these leaks to recover the secret key. This is referred to as side-channel analysis, and it can be implemented on any device that uses cryptography to protect its secrets, ranging from smart cards, SoCs, and FPGAs, to mobile phones, tablets, PCs, and servers. Let's take a look at how side-channel analysis works. This board includes an FPGA. FPGAs are programmable chips that are often used in systems for government, telecommunication, networking, and security. This development board is specifically designed to test the side-channel resistance of cryptographic algorithms implemented in the fabric of the FPGA. We will begin by encrypting a block of data on the FPGA board by using the popular AES encryption. This encryption algorithm uses a 128-bit input and a 128-bit key, but internally it only processes them in 8-bit chunks. Since our plaintext is much larger than 128 bits, the FPGA uses a common chaining mode. This generates a power consumption trace of 10,000 chained AES operations. If we zoom in on the scope and focus on an individual AES operation, we can clearly see the 10 rounds of AES. At each point in time, the power consumption depends on the activity and the intermediates that are being processed in a round. But since these traces are noisy, one single AES encryption will not give us enough information to reveal the secret key. However, if we combine multiple AES operations using statistical techniques, we can use them to check a series of key guesses and begin recovering the key. Focusing on 8 bits at a time, we'll look at the AES operation, which consists of 3 variables: the input, the key, and the SBox table entry. If we guess 8 bits of the key and we know the 8 bits of input, we can predict the other variable, and we can correlate it against the 10,000 AES operations and the 10,000 corresponding ciphertexts. If the key guess was wrong, then the values being predicted are not related to anything that's being done within the FPGA. So there will be little to no correlation between the predictions and the power traces. If our key guess is correct, then the FPGA will process the correctly predicted intermediates, so the power traces should correlate with the predictions. Here we are predicting the 8 bits that go into the 15th SBox table lookup. This trace is a correlation for key guess equal to 0, and as you can see, the correlation is low. If we look at the correlations for the other key guesses, you will see that they are also low, but as a right key guess comes along, we see a big correlation peak. Once we have the 15th byte of the key, we can repeat this analysis, using the same 10,000 traces for the key byte involved in the 14th SBox lookup, and so on, until we recover all 16 bytes of the key. An attacker can easily automate this entire side-channel analysis to recover the key in only a few seconds or minutes. Once the key is recovered, an attacker can steal data, forge identities, make fraudulent transactions, and even modify the device for other illegal activities. At Cryptography Research, we help customers defend against side channel attacks by using countermeasures that can be applied at the software, hardware, and protocol layers. In fact, our patented DPA countermeasures are deployed in over 6 billion devices made every year. For more information about side channel analysis and how to secure your products, visit us at cryptography.com.
Using the basic pattern traces for the device involved in the portion, and so on, until we recover all 6 devices. An attacker can easily automate this entire side channel network to recover the key in only a few seconds or minutes. Once the key is recovered, an attacker can steal data, forge identities, make fraudulent transactions, and even modify the device.
So that attack uses statistical methods called correlation. If you have learned stats in the university, you might have come across this statistical technique called correlation. I'm not going to go in detail. So look at another type of side channel. So we look at power analysis, electromagnetic emissions, and you can even steal information using sounds generated by the computer. So what kind of sounds that you are listening, right? If your computer is working, when processor is working on data, processor consists of several million transistors, right? These transistors turn on and off in very fast. When the transistors turns on and off, it draws power, right? Variable amount of power. So there's a power supply circuit that gives power to the processor. It tries to regulate the power when processor is requesting varying amount of power, right? It has capacitors and other equipments inside it. So people have found that these capacitors make high frequency noises. Actually, it's not, people are not able to listen that, people can only listen to 1 hertz to 20 kilohertz, right? These are basically in 40 kilohertz range. So we can't directly listen, hear them, but these capacitors and other electronic computers in the power supply makes these noises. We can use these noises to extract useful information about what is going on inside. So here they are trying to listen to that computer in the other corner of the table using parabolic microphone. Using this parabolic microphone, you can listen to distant sounds. People like bird watchers uses these parabolic microphones. So this is what they have recorded. So they made that other computer run RSA decryption operation and listen to the high frequency sounds made by that computer and recorded it. So this is called spectrogram. Right? When you have any sound, any wave file, any sound wave, you can separate various frequencies that make up this sound wave. Right? Any sound is made of number of different frequencies. It's collection of number of sound waves with different frequencies. You can mathematically separate these frequencies using techniques like fast Fourier transformation. So this spectrogram has frequency in x-axis and time in y-axis. This is how we draw the different frequencies. Now this yellow arrows point at the middle of RSA operation. If you look at if you look at details of RSA, it uses 2 primes, P and Q, right? It first use P and do one process, and then use Q and do another process when it is decrypting any data. So you can see this strong frequency component when RSA operation is using P, and this one when it's using Q. This is another RSA operation. It's using P here and Q there. P and Q, right? So RSA operation has two major phases. You can directly see those two major phases in the audio record, spectrogram of the audio record. So how can you retrieve the key using this information? What you can do is you find the secret key bit by bit, right? You craft the ciphertext so that this acoustic leakage only depends on one bit of the secret key. That's possible according to RSA implementation. Right? Then you trigger decryption and record the audio. So if you have a strong component, then you draw the spectrogram. Right? If you have a strong component around 35.2 kilohertz, you have bit 0. That bit is 0 with the key. And if you have a strong frequency component around 38.1 kilohertz, that bit is 1. And you can, by just listening to the sound made by the computer, countermeasures that we can develop against this kind of tech. You can use sound damping frequency, you can make artificial noise so that attacker can't extract any useful information. Also, you can use software techniques. This is another side. Heat made by the electronic components being operated. This one experiment people have done. So there are two different computers. One computer, they have connected toy missile launcher to one computer, and using another computer placed nearby, they command the second computer to activate the top as an experiment. If you have any high security environment, people normally do this. They air gap compute. Air gap means there are computers that are not connected to internet, or there are computers that are not connected to networking before, right? But if there is a computer that is connected to network nearby, you can even transmit the data to the network computer by using heat, right? So these computers have built-in heat sensors. If you run a heavy process in the processor, heat goes up. If you lower the processor load, heat goes down. And that is, heat can be detected by the sensors installed in the motherboard of the nearby computer. That's the basic idea. It's only a demonstration, but they have done demonstrations. All is launching missiles. All those commands are given by the first computer. Only using the non-network connection whatsoever. I'm not sure whether you completely understood it, but I just wanted to introduce these concepts and start your interest so that you can go and find more information.